Now I said there is a total of 3 options on how you can determine the net force. So this was the first one, the graphical one. So here's the second one on how to compute it. Well, we have 1000 newtons for the thrust to the right and 500 newtons and that drag of course is pointing to the left, so we subtract that. So in the horizontal we have 500 newtons. In the vertical we have 6000 newtons for the weight, and we have 4000 newtons for the lift, and they're in opposite directions, so we subtract those, 2000 newtons. So the 500 was to the right and the 2000 is down. And now because we have them in 2 different directions, and this here would be a net force as we know from the graphical method, we would add them with the Pythagorean theorem. So we have 2000 newtons squared plus 500 newtons squared. And when I said they're in 2 different directions, what I meant to say was they're in 2 different directions and perpendicular to each other, so we can use the Pythagorean theorem. Okay, I'm going to calculate that. So square root of 2000 squared plus 500 squared, and that equals 2061 rounded 2100, or if I just had one significant figure, which I actually kind of do, just 2000 newtons. And of course the 2200 newtons earlier was kind of an estimate. You can do it either one of those two, or you can do it the third way that is coming up, and that is this web page, this applet that I posted in the lab, which I believe is really good. And notice what it's doing, numerical vector addition. It's doing exactly what we've been doing here, and probably even more accurate. Okay, so I put the first vector in at 1000 newtons, and it's pointing to the right, which on the circle means 0 degrees. But notice that my vector here becomes really long when I put in 1000 newtons, and therefore it's advisable for these setups, when you use this particular applet, to scale all these vectors to hundreds. So in this case I take my 1000 divided by 10, so I have 100. The second vector was 4000 newtons, but I scale it down to 400, and it points up at 90 degrees. See, even that gets off the screen, but if I scaled it down to tens, it would be actually worse. Now I'm going to add a vector. I need the drag vector, which in this case would be 500 newtons. Respectively, I scale it down to 50, and it's pointing to the left, which is 180 degrees. And finally, I have the weight, which is 6000 newtons, and I scale this down to 600. Straight down, which is an angle of 270 degrees. There we go, and now I move this in here. And then, as shown earlier, the net force is from the tail of the first one to the tip of the last one, and this number here we had just calculated. So that would actually read 2061 newtons. So 2000, 2100, earlier estimated 2200. And it points to the lower right. Besides that, it says 284 degrees. We can see that, and we saw that earlier in the first graphical method. So use any one of these three options. This one here comes in more handy more often than not. Here's the other setup that I want to use as an example. And it says the same two-door front-wheel drive sedan of mass 900 kilograms got off the road, now travels with a speed of 50 kilometers an hour to the right on grass and encounters a bump on a meadow. So that's what we got here. And we have a number of force vectors. The scale is 1 square equals 1000 newtons. Notice though that my squares are relatively small. Here's the weight, and of course you do have the rulers on the sides. And so here, for example, it says, okay, from 2 to 10, but then there's an additional square, so that's 2 to 10 is 8, plus that 1 is 9, so the weight is 9,000 newtons. Makes sense, of course, because the mass is 900 kilograms, then the weight is 9,000 newtons. So that's the weight. Then here we have a force of, that kind of looks like 6,500 newtons, and I would call it simply the engine force. That's what gets the car forward, in this case to the upper right, because it's on this bump, and it's at an angle of 45 degrees, and you can measure that with a protractor, and I can measure it right here, and it looks like 45 degrees. Then here we have a support force at 9,000 newtons to the upper left. Here we have friction at 3,500 newtons to the lower left. Here we have friction at also 3,500 newtons to the left. And here we have a support force of 4,500 newtons up. And again, I'm pretty much just looking at the squares and count the squares, how many I have. And as I had mentioned on the lab sheet, what I'm trying to do is get to either one full square or one half square. So don't read too much more detail into it. So when I said on this one here, that was meant to be 6,500 newtons.